doubt if nowadays you can publish a scientific paper without having all of these steps in your paper. So you have to pay attention to some of it. So I will try to define some of these concepts so that we all have the same sort of ideas about what they are. But calibration, as you know, is just to adjust your model parameters and your model structure or your variables, whatever that you have, so that you achieve the best simulation. Right? That's what you want to do at the end. You want to have the best simulation, the best match with what model gives and what observation that you have. So that's the idea behind calibration. And then calibration, most of these automatic calibration tools that are now available, at the end, they boil down to optimization of a certain objective function. Okay? Please pay attention that the calibration at the end becomes a mathematical exercise in optimizing a certain function. And that function, which usually referred to as objective function, could be some kind of an error. That's the observed discharge minus simulated discharge. So you want to minimize this. So you want to minimize this. And there are many, many different types of objective functions. If you look in the literature, there are a lot of different types of objective functions that you can use. But the ultimate goal is to minimize such an error. And not only to minimize the error, but to catch the dynamics of your observation and so on. So that's why you have different objective functions. Now, there are some problems arise from this fact that there are many different objective functions, and I'll explain what they are. Now, validation is once you have calibrated your model, you use a certain amount of your observed data, usually you use a certain amount of it to calibrate, then you need to show that your model actually is not just conditioned on those observed observations that you use for calibration, that they can also simulate beyond that input that you use to calibrate the model. So you need to always to save part of your data to validate the model. And then once you calibrate it, then without any further adjustment to the parameters, you need to just run your model and make sure that, or at least see that how it behaves during the validation period. So validation is sort of an independent data set from what you use for calibration. Now, sensitivity analysis. Why do we need to do sensitivity analysis? Now, this is a process where you define which one of your parameters have the highest impact on your output or on the objective function that you are using. And usually we would like to know that for many reasons, but one reason is that, as you know, parameters represent processes. So you would like to know, for example, what are the dominant processes in your watershed. So you would like to know which are the most sensitive parameters. So those parameters, from whatever function they come from, are then the dominant processes in your watershed. And a good example of this is this CN2. As you know, CN2 is a factor that sort of partitions the rainfall into infiltration and runoff. That's a very important parameter. And if you do some sensitivity analysis and you change the value of CN2, you see such behavior. You see, as CN2 is minus 0.6, this is some kind of a relative factor. So it's a very small value. Small CN2, you see the blue. You have very small peaks, you have almost no peaks and so on. And then as CN2 increases, you see what happens to the peaks. So if you're not able to catch the peaks in your observation, you know which parameter to go to first. So that's why we do the sensitivity analysis, to determine these important parameters. Then you come to uncertainty analysis. Now, uncertainty analysis is the uncertainty analysis is the process of propagating the uncertainty in the model through the model and to see its output, what the impact it has on the output. But then you need to quantify the magnitude of uncertainty, and then you use this uncertainty for many other further analysis, such as risk analysis and so on. You need to know the uncertainty of your model. But basically, the uncertainty comes from the fact that we don't know what the parameters are beforehand, or that our measurements are very small, number of measurements you make, or that the heterogeneity of the system is so large that even if you take 100 soil samples and determine hydraulic conductivity, you still don't know what hydraulic conductivity of your soil is. Now, usually, you will see in the literature sometimes, older literature of course, that they say calibration and uncertainty analysis are two different processes. They're different from each other. But now we know that uncertainty and calibration are really so intimately linked that you cannot separate them. So if you come and tell me, I have calibrated my model, I will ask you, okay, what is your confidence on the model that you have calibrated? Then for that, you need to show me the uncertainty, and you propagate that through your model, what sort of output do you get. Now, I will talk much more about this, but to show you, to make the point, if this is your observation, and then you go and calibrate your model, and you get something like this, and you may say that this is the squared nice fit of your observation. And then you may recalibrate the model and get another curve like that, and then you may recalibrate the model again, and you will get another curve. These are all different from each other, and the parameters behind these curves are quite different from each other, as I will show. But then they are more or less just the same good as the other one. One is as good as the other one. It's very hard to say. So that's why when you say I have calibrated my model, I would like to know how many of these curves there are that give you rather good solution to the system. That is the non-uniqueness. The output from inverse modeling, or from calibration, also known as inverse modeling, is not unique, is non-unique. So I need to know how many such curves there are that are really good solutions to your model. So just to make a point, as I said, there are different objective functions that you may use to calibrate your model. Now these objective functions are sort of tell you about the performance of your model. So you do some kind of an index, an indicator to the performance of your model. And there are many different ones. There is root mean square error. I will show you later some of these. There is R squared, of course. There is Nash-Sutcliffe. There is BR squared, and so on and so forth. Now you see, if I these curves come from different use of different objective functions. So if I look at the root mean square error, and there are about 5 different sets of calibration here, and you look at the value of root mean square error, you may find that this is the best one, but this is not too far off from this one. And in fact, if you do a statistical test of comparison of the significance of the differences here, you will see that statistically they are not different. So that means any of them could be a solution, really. Or all of them could be the solution to your problem. If you look at R squared, you see that different sets have different R squares, and this time, this is set number 2 has better R squared than the other ones. So if you use similarly Nash-Sutcliffe, you will see that set number 3 is the best of these, and so on. So you see that if you use different objective functions, you will come up with different sort of best solution at the end. Now, which one is better of all these bests? So that's a question. Now, if we go, maybe this by itself is not a problem, okay? So we have many solutions. We quantify all these good solutions. And then you go back and you look at the parameters that gave you those solutions. And these are some of the SWAT parameters, as you know. If you look at CN2, you see it ranges. Again, this is a relative number. This multiplies your actual value of CN2. So you see that it ranges from minus 0.2 to plus 0.3. So that means your watershed is actually switching from an infiltration-dominated watershed to a runoff-dominated watershed. Very different processes. They give you the same good results. And if you look at all the other parameters, you will see that some of them have really large differences. So that's where the problem is. The problem is that different sets of parameters can give you similarly good results. And then you don't know which one is better. Which one is better. And they all have a different story. There's a different story about your watershed. So that's one problem you need to keep in mind. That's why I say calibration and uncertainty analysis, they're linked. You cannot separate them. You have to show both. Now, there are a number of issues with respect to calibration of distributed watershed models, and that we really need to keep in mind. Because it's too often that we just take, build a model, do some parameter changes, get some result, and then you think that now you have calibrated my model, now you can take it and do whatever you want with that model. It's not that simple. So you, as an analyst, you really have to be careful what you're saying and what you're doing. Especially if there's management involved, especially if it's more than just an academic exercise, you really need to pay attention to a number of things. Now, some of the problems, and I will discuss these one by one, is about parameterization. This parameterization is really very, very difficult to do because you're dealing with a large area, often a watershed, and there is a lot of heterogeneity involved, and how do you assign parameters to different HRUs and so on. That's an issue to think about. Then you have this objective function definition, as you saw. Objective function, if you change your objective function, your end result will be completely changed. That's a problem. Then the non-uniqueness or the uncertainty. So if you have one good solution, then you have thousands of good solutions. You know, how do you deal with that? Then you have the so-called parameter conditionality. Parameter conditionality is for your watershed, you use a certain model, or you use SWAT. You have used a certain input data to calibrate your model. You have made certain assumptions to build your model. So many things, you have used a certain objective function, you have used certain weights in the objective function, you have made a lot of assumptions to calibrate a model. At the end, the model that you have reflects all these assumptions. So to use that calibrated model outside the range of these assumptions, you have to be very careful. You calibrate a model using river discharge, and now you want to estimate sediment. It will definitely not work for you. I can tell you that. Because you didn't calibrate your model using sediment. You need to have sediment in there if you want to predict sediment. So you have to be careful at the end, how do you use the model? A big problem, this comes out of two of our projects. We have a project in the Black Sea and a project, the Europe-wide project, to actually build a model for the whole of Europe. And there are so thousands of, outlets involved. And these outlets are partly observed outlets that you have to put them exactly where you made the observation, right? But often, if you have slightest error in the coordinates of that outlet, they go on the wrong river or the adjacent river, or instead of being on the main river, they go on a tributary of that river. I will show you some pictures after. And that creates major headache for calibration. You have a river which is on a tributary river with a discharge of about 100 then your observation is about 1,000. That actually should be on the main river, should be on the Danube, but it goes on some tributary of Danube. And you have a big difference here, and there is no way by calibration you can fix this. So you will always have problems. So positioning this observation, it may not seem very critical, but it's really quite critical when you come to a larger watershed. I will show you some pictures now. And finally, there is time constraint. So I often get emails from students, especially master students. He says, look, I have 2 weeks to finish my thesis, and I can't get my calibration right. Can you help me out? So we have very little time to do something big. You may spend actually 2 years to build your model, then you want to calibrate it in 3 days, and that doesn't go. You need to spend some time to calibrate. And if you have a larger model and SWAT takes 1 or 2 hours, or in our case, 37 hours to run, then there's no way you have enough time to calibrate that model. So often we make some runs and then we sort of say, okay, this is calibration. So that's a problem, time constraint. Now let me go through this one by one, and just to highlight some of the problems that may happen, and you can take some steps to avoid it from the beginning. One is with parameterization. And I often use this soil map example. You see this is a watershed in Switzerland. It's a 2 watershed in Switzerland, and you have the same soil here, and then it appears here, and it appears here, and all over the place. You have the same, you take a soil map, and you know that this is actually a mountainous area, and then you come to a flat region, and there's forest here, and it becomes very agricultural here. So as the land use changes, even though you have the same soil unit in your soil map, the soil properties will change. I mean, the same soil under forest, it doesn't have the same hydraulic conductivity as the same soil under agriculture or, pasture or so. So how do I do that? My soil map gives me the same value for hydraulic conductivity of all these units. But I know that they cannot be the same. They're different. So if you go from, on the one hand, you may try to define every HRU with a different hydraulic conductivity, and you make millions of parameters there. Or you may lump and sort of lose your heterogeneity of the system if you lump too much. So you have to find sort of a balance between the number of parameters and how much you want to lump and lose the heterogeneity of the system. So this is really something that you need to think about. I don't have a solution of how this is, but in the tools that we try to create with this SWAT cup, you're given the option to actually parameterize down to HRU, every parameter. So it's up to you as an analyst to determine how much lumping you want to do. So I explain what these are. Every parameter in SWAT, almost every parameter in SWAT can be specified or as you can see here. There is a certain factor here, is a qualifier that if you use, it can be V, A, or R. If you use V, that means you want to replace this parameter with a value. You want to replace a value of the parameter with another value. If you specify as A, that means you want to add something to the existing value. And if you use R, that means you want to multiply the existing value with a certain number. Now, why do you do this? Because in calibration, basically the basic main step is you change the parameters, you run the model. You change the parameter, you run the model. You change the parameter, you run the model. And then you analyze this output. So we have to find a mechanism for changing the parameters. So you have a certain default model that you build at the beginning. You have a value for every parameter, and then you want to change that value and then run the model and see the impact of it on the model. So these are 3 different ways that you can upgrade or update the value. You can either replace a value with another value, or if you want to keep the same sort of system, you can scale everything up or down by multiplying it by a certain number or adding something to the existing value. And they each have, depending on the parameter, they have an application. We can talk about it later. So, parameter name and extension. As you know, all SWAT files, input files, go into these text files, and you have extensions .sol, .hru, .rte, blah blah, and you have all these. That's that extension, and that's the parameter name. So this is the parameter name that resides in that file. And then you can change this parameter based on the hydrologic group, based on soil texture, based on the land use, based on the subbasin number, or based on the slope. So you can see, to give you some examples here. For example, hydraulic conductivity. So if I write, I want to do a relative change to hydraulic conductivity of the first layer. And you may have many layers that you can change hydraulic conductivity of every layer individually. Of the first layer. Or you want to change the hydraulic conductivity of layer 1 to layer 3. So these are all the different options that you can characterize this. Or you want to change hydraulic conductivity of all the layers. Or you want to change hydraulic conductivity of layer 1 when the soil texture is fine silty loam, only for this soil. Or you want to change hydraulic conductivity of first layer when the soil is fine silty loam and the land use is pasture. Or you want to change hydraulic conductivity when the land use is pasture and for subbasin number 1 to 3. So any combinations of these, you are able to change the parameters. So you can really go down to every HRU and start changing to see what happens of the parameters, or you can lump them. And here, you want to change hydraulic conductivity of first layer only if it is on the slope of from 0 to 10. Only for those. So you have a lot of options in how you want to parameterize. You can do that for almost, I say all parameters in SWAT. These are management parameters. Management is a little bit more complicated to handle. So you have rotations, you have operations. So you specify every management parameter by rotation number and operation number. And you can have some filters that you can see this for a rotation number 2, operation number 1, when plant ID is this, number 33, or you want all rotations, operation number 1, that would be a planting. When the plant ID is 33, you want to change this parameter for that. You can even specify certain file of SWAT to do the change. So you have sort of unlimited option really to how you want to change the parameters. I included rainfall. Rainfall is a driving variable. It's a very important input parameter. And as you saw this morning, you have this WGen in SWAT. You can calculate the statistics. And then from the statistics, you can simulate a number to fill all the missing data and so on. I added this. You can adjust any rainfall for a day or for a number of days or for many rainfall stations and so on in any way you want. But I really added this. I was very uncertain, unsure about whether I should add this capability or not. The reason is that if you can fit the rainfall, you can fit anything, basically, right? Because rainfall, you can create any kind of shape you want, discharge from the rivers, if you're able to fit the rainfall. So you really have to use this with caution. You can't just go and, if you cannot catch a peak, then just go and increase the rain on that day and you will catch a peak, no problem. But on the other hand, some people wanted to have this option because what SWAT simulates is just a simulation. And it could be really very wrong sometimes because you're just simulating based on statistics, albeit good statistics, but you make the simulation. And that could be anything. So you should have the option to change a certain rainfalls, especially the ones that you have missing data, as SWAT has filled it with some simulations. So the option is there, but you have to use it with caution. The same with temperature, you can also change temperature. And then there are crop parameters, you can also change crop parameters in the crop file, any kind of parameters and so on. And all the other files, you may be able to change the parameters. Now, by parameterization, what happens by parameterization? Say you have a set of parameters, you have CN2, you have alpha base 2, and so on in your model, and you're adjusting these parameters, you're trying to calibrate using these, and then when you parameterize, you may, the reason for parameterizing is this, so this is your watershed, and this is the example that I will show you later. And so you can see that, for example, at this point, you only have this subbasin number 14, 18, 19, and 20 that feed that outlet there. So there is no reason for changing the entire watershed just because you want to catch your observations here. You can only change these. And then as you're coming, and that's the outlet, so you may want to change the parameter, and you have an observation here, you have an observation there, and an observation there. So you may want to just change the parameters here in order to catch the observation at this point. And then from here to here, I'll feed this one, so you only want to change these ones for that, and then the rest for that. So you see, you may want to parameterize your model so that these parameters can adjust differently from those parameters and then from those parameters. So for that, once you parameterize your model, you may end up with something like this. So you may have a CN2 of those subbasins. They can vary in that limit, and CN2 of subbasin number 1, this is by itself. The subbasin, nothing goes into it. They may vary by different margins, and these subbasins of the rest of the watershed, from 8 to 13 and 15 to 17, may be different ranges. Depending on the land use and so on, or other information that you have, you may want to adjust the limits by which these parameters can change. So if you know that this is a mountainous really region up there, and you have more runoff there than you have infiltration, so you want to have a higher value for CN2, for example. So if you have any information about your watershed, you can use that to determine these ranges. So that's how we do it. You say this parameter for those subbasins, it should change from minus 0.5 to minus 0.1. So this is an initial range that you say you want to change. You want that parameter to be changed within this range. So what the program does, and then you want to simulate this 1,000 times, the program will take 1,000 samples from these ranges, and then run them one by one, 1,000 times, and then at the end get all the outputs, and then try to analyze those outputs. So that's a basic procedure that I would do. So here, you see with parameterization, you have a lot of flexibility to define your parameters, or a bunch of parameters, or lump them as you wish, by soil, by land use, by subbasin number, by slope, and so on. So that's up to you to determine how you want to parameterize. Now the next was objective function definition. And so I know I'm going a bit fast, but you guys are not stopping me, so I just go. Objective function. There are many different types of objective function. You know, this is the mean square error that you may have different variables in the objective function. You may have discharge and sediment and nitrate. You want to simultaneously. It's a multi-objective function you can build. And in this case, they have different weights. if you add them together, because these is maybe around the hundreds, that would be around 10,000s and so on. And if you don't have any weight, then that will dominate this objective function, and then it will have very small impact, the discharge. So that's why you have to have weights if you're using this type of objective function. And then there are different formulas for calculating the weights, and if you use different formula, you come up with different weights, and then at the end you come up with different answers. So to avoid using the weight, you multiply them together like this for the multiplicative sum of square errors, or you may use Nash-Sutcliffe, very popular. They each have advantages and disadvantages, all of these that you need to know. The disadvantage of Nash-Sutcliffe, for example, is that if you make 1,000 runs and one of them if they are a combination of parameters that give you very bad Nash-Sutcliffe, then that will dominate your objective function. So you may have minus 300 or minus 500, and that will dominate it. That's the problem with Nash-Sutcliffe. And then you have other kinds. You have R squared. R squared has certain advantages and certain disadvantages. I think the disadvantage of R squared is that if you have observation and you have simulation like this has R squared of 1. Whereas the magnitude can be very different. R squared captures the dynamics, but not really the magnitude. Doesn't care about it. Then you may have chi squared and BR squared. BR squared is a good substitute for R squared. B is the slope of the regression between observation and measurement, and that takes care of this magnitude.
Repeat the slopes between?
Sorry? Between observation and simulation. It's the slope of the regression line, and if you multiply that by R squared, you try to capture this problem. So we have been using this quite a lot. It is very good. And then there are things I added recently, this p-bias and RSR. And so there are all kinds of objective functions, and there are more. I will add some more to it. And the idea is, with SUFI 2, you have this option that you run 1,000 times, 500 times, and then you can just change the objective function and calculate and do the post-processing with the objective function quickly. So you can actually see what the different objective functions are doing. Once you have done the main run of SWAT 500 times, then you can change the objective function and right away see its impact. I'll show you. This is another one. This is a ranked sum of square errors, and you use this if you care only about the distribution. You don't care about one-to-one, match between the observation and simulation. Then you can get a very, very complicated forms of objective function, and you can read about this in the paper. We had a PhD student who worked on this, and then and there are many more. And there are many more, and the problem, as I said, is that if you use different objective function, you end up with different solutions. All right. Then you have the non-uniqueness. That is, you don't have one solution. And the reason is that if you use a direct or a deterministic modeling approach, you give input to the model and model gives you an output. That's clear, no problem. But if you want to go the other way around, you want to use the output and you want to estimate your parameters using discharge and nitrate concentration, then you have the problem. Then it's inherently non-unique. Then there are many different solutions that give you the same sort of results. So that's a non-uniqueness problem. And I showed you this before, something like this. So you have the observation is the red one. You have the two very good simulations. If you look at the objective function, you see they're almost really the same value, g at the end. Same value objective function. You look at the parameters, and you see there are very different parameters, gives you the same good result. That's a non-uniqueness problem. Why is it like that? This is some theory that it's called the Swiss cheese effect. You've seen Swiss cheese. It's there. It has all these ambiguous holes in there. Nobody knows where these holes come from in the Swiss cheese. You may know. If you look at the surface of the objective function, it looks something like Swiss cheese. Now here is the objective function, but I inverted it so that all the low points become peaks. Just you can see it better. You see, all these peaks are really good solutions. And these are two different parameters that are changing, but in reality there are 4 parameters changing simultaneously. So I just plotted 2 of the parameters against the inverse of objective function. So you see, all these peaks are good solutions. So if you use different objective functions, if you use different programs, different algorithms, I'll show you different algorithms for using, they each converge to one of these peaks. They all find good solution because they're just, that's the way it is. That's the surface of the objective function. It's peaky like this. And every program, every methodology converges to one of these peaks. And then that's the solution. But in reality, you have many good solutions. So you sort of have to, if you want to really capture the full uncertainty, you need to capture all these solutions. So your end solution should be a combination of all these good solutions. But that may be really impossible to do. Now, the parameter conditionality, I mentioned before that at the end you get a set of parameter ranges for your calibrated model, and that is a function of how you parameterized your watershed, the type of objective function you use, the weights in the objective function, the whole conceptual model. You used SWAT. SWAT has many options. You can turn off and on different functions, and it's on the experimental procedure that you collected your calibration data, especially for sediment. For sediment, the different ways of collecting, it's not an easy thing to collect observation of sediment. And in the Tour watershed, they had in Switzerland collected data for over 30 years. And Swiss style, you know, it's very detailed and very careful. At the end, they realized that the instrument that collected samples in the river was in a river that had more turbulence than other parts of the river. So, overestimation of anyhow, so that and the input, the driving data that you use to calibrate the models, the types of variables and the location of outlets, so anything you can think of. So your model is conditional on these. So you have to make sure that when you want to apply it, when you validate it or apply it, if you go too much beyond these, what your assumptions, you may get anything. And that's an example of this conditionality. This is actually a good example because this is the same Tour watershed in Switzerland and in the northwest of Switzerland. And this was the first, actually, one of the first things I did with SWAT. And we were given the Swiss, since 1970s, they had measured all the rivers that leave Switzerland into other countries. They measured water quantity and water quality. They have a very good database. So, and we used it here to see at the beginning how well SWAT does, and they also wanted to dismantle some of the observation points and put new ones and so on. So we did some analysis, and they had observation at the outlet of the watershed. So I used that and made such an objective function with discharge, sediment, nitrate, and phosphate, and calibrated the model. It went quite well. The model was calibrated. And then I used the model. They wanted the loads that came from different land uses. So you had pasture, forest, agricultural, so on and so forth. I calculated the loads from different land uses, and they totally disagreed with those loads. because this is what they have measured. That nitrogen from the forest should be between these two numbers, and from agricultural should be here, from pasture should be here, the same with sediments, with phosphor, and so on. And so then I use these as I use it as constraint to this objective function, and recalibrated the model again, and again came up with a different model with different parameters and so on. But this more or less the same good results as before. And here you see the daily discharge. The shaded region is the 95% prediction error of the model, prediction uncertainty, and that's the observation. See, it was really quite good. And then for, this is bi-weekly sediment. For sediment, you see there is larger uncertainties, and this is the observation. Still, the dynamics is there and so on. So it's not as good as this chart, but it's still quite all right. And then when we investigated a bit more, that why it was higher uncertainty and so on, and this is what we saw, and this is about the model structure. The structure. In SWAT, you have the universal soil loss equation. You know how good is that? Here you can see that this is a discharge, the red one. And so here is there is nothing happening, and then you get a storm. And then some days later, you get another storm. And then the dashed line is the simulated discharge, and the blue line is the observed discharge. So here, for the first storm, it was quite good, the observed and the simulated. But then in the second storm, simulation is over here and observation is over here. So our idea was that when the first storm comes and mobilizes the first layer of the surface and moves, it's okay. But then to mobilize the second layer is more difficult, to mobilize the second layer. So for that, observation is over here, but the model doesn't know that. You know, the model doesn't know that. So the model gets quite a bit of overestimation for that. So we call this the second storm effect, and there's something about the model structure that can cause uncertainty. And then furthermore, after I calibrated the model and all that, we got some more data points from inside the watershed. And I used the model to see how good they were. They were quite good over here, and they were quite full down here. So again, so we thought we had a good calibrated model. So again, so when you go to the next higher phase of analysis, you see that it's not that good really. It's good for parts, but it's not good for over here. So what I need to do, I need to again use these and recalibrate the model. And then once I do that, then maybe I get other variables and so on. So here is the end to this calibration. Seems to be, depends on what you want to do. Depends on probably no end to calibrating a model. So a calibrated model is always conditioned on the situation that it was calibrated for, and care must be taken to apply it outside of that boundary. Now, positioning observed outlets in SWAT becomes really a problem sometimes, and for different reasons. One is that you may get the outlet completely on a wrong river, and this happens very, very often in our large Black Sea and European models. And the other thing is that you see the outlet may be just downstream of a dam where water is managed. It may be near to a glacier, you know, that it's fed by the glacier bed. And I don't know now what is the situation of this glacier component in SWAT, but it wasn't that good before. So when you come to these situations, this is really causes a big headache to calibrate the model, you want to calibrate for that outlet, then it's really controlled not by natural condition and rainfall, it is controlled by the operation of the dam. So this causes a major problem. So you need to be able to identify, where these outlets are. And if you have a small project, yeah, okay, you can go there and you know where it is. But if you have a larger project and you don't really know where it is, then you need some kind of a tool to look at it. So we have in the program, there is an outlet map here. I will show you that you can actually go and observe every outlet and see what the land use around is and what is the situation. That gives you more information, better information, how to parameterize that outlet and so on. Here is some example. You have this situation somewhere, I think somewhere in Europe, 5842. I should remember that. We can have a look at that after. 5842. You see the outlet is positioned here, but it's not at all there. It's somewhere here on the river. There is no river over there. And if it is here, I don't know if it's here or here, maybe. If it is here, then you really are under the influence of this reservoir here and operation. So there is no way, you can see, this is the best simulation, and this is the observation. So you see, it's not very good. The simulation is not very good, and you can never make it good. No matter how much you change the parameters, it's not going to capture that. And that really sort of, if this is one of like your 10 outlets you have, can really screw up the whole calibration, Finally, there is time constraint, and for time constraint, we tried to do something about it, and then it became something. But anyhow, there is a sort of an algorithm, a sort of sub-program called the parallel processing that we added to the whole procedure. Well, a company actually did, and they are in charge of this, and I'm trying to, and this is a licensed product, so you need to buy it actually to be able to run it. And what it does is that it uses the number of CPUs you have in your machine, and these newer machines have probably 4 to 8 CPUs. And instead of submitting one job, you can if you have 8 CPUs, you can submit 8 jobs. And so it can speed up quite a bit the whole procedure of calibration. So you can make, instead of making 1,000 runs, if you have 8 processors, I don't know, you can submit 125 jobs each, and then really cut down on the time. It's a good program, but right now it's licensed. So that was sort of a very short introduction to the problems that you may encounter with calibration. And I would like to spend a bit more time on this uncertainty and then get into the concept of the program. But I'm not sure when we have to stop, because I probably get too much information.
In 15 minutes there's a coffee break, so 3 o'clock coffee break.
It's about coffee break now?
I know, at 3 o'clock.
At 3 o'clock?
Yeah, another 15 minutes.
Another 15 minutes? Okay. So you guys have any questions, any comments, anything?
It's all right.
That's okay.
Comments.
Yes.
No, please, sorry, I haven't seen you before.
Good.
The ranges, randomized ranges are each parameter.
Yes. Yes.
It runs once at a time. I mean, it finds the better in the first range and then proceeds with the others, or
Yes.
it's a combination.
Mm-hmm.
How does it work?
I'm slowly getting into how the program actually works. But yes, every parameter has a certain range at the beginning. You have a certain range based on literature, and nowadays many papers report initial and final ranges for the parameters, so you can get it from the literature or based on your own judgment or whatever, or you look at the There is SWAT gives you a range itself, and so there are a number of sources where you can find the initial range for the parameter. And then so you have, say, 10 parameters, and they each have a range. Then you sample these ranges. You may sample 200 times, 500 times using Latin hypercube. I will show that. It's a sampling procedure. Normally, I mean, the simplest way to sample is Monte Carlo. Monte Carlo, where you take random sample from each, you make 1,000 random samples from these 10 parameters, and then you run your model 1,000 times. But there are more efficient methods than Monte Carlo. One of them is Latin hypercube, that is more efficient, and I'll show you how that works. But you take a number of samples, say 500, 1,000 samples, and then you run your model that many times. You analyze the output, then you come up, that's called one iteration. One iteration. And then you identify new parameters with narrower ranges based on the analysis, and then you do another iteration with parameters that have narrower ranges and they shift, up and down. So you do a few iterations like that until you zoom in to one of those peaks that I showed, those many peaks, to one of those peaks that you get some good solutions to. That's the procedure that I'll show you this. Yes, you have a question.
No, it's okay.
Okay, you have a question or somebody there have a question?
But before you get into this calibration, you want to definitely check all your inputs at the beginning to make sure you have provided the best input, possible inputs, okay, before you start. I mean, let's say, for example, the overall rainfall runoff ratio should be, say, 30%. And your model is saying 60%, overestimating it. There is no way that you are able to bring that down to an agreeable limit, actually, when the salary is so high. Right? Your output transmission is so low. Unless your plant is growing, you are not going to do any of this stuff. I mean, that's not the physical parameter. If you choose the right plant, when you plant it at the right time, if it grows when it's supposed to grow during the summertime, those are also physical parameters that you have to check. So that's what the SWAT check program will help you to at least look at the overall picture. Once you got somewhere, say, 20–30% of your observation above or below, then a program like this can help you to narrow that from 20–30% to maybe 5% or 10% within the observation. But if you start with a very large gap between your observed and predicted data, there is something wrong with our input. So it's not that magically we can somehow fix everything through the uncertainty and the RSR. So very, very careful. So if you start doing that kind of analysis, that means we are not controlling our own watershed. Maybe we didn't understand what's going on in the watershed, and we start doing this calibration and stuff like that. So you can be chasing around, but you're not going to get the final solution of what you want. You may get a solution, but you may not get finally what you want if you're not careful at the beginning. So.
Yeah, exactly. That's excellent comment, because you need to start, if you start with a very poor model, you will not solve it by calibration. You really, at the beginning, need to put your best estimate of the parameters in the model, and at the very, very beginning, I have now written a procedure, a protocol, the step-by-step how you can do. When you do the first simulation, with your default model, you can come to the tool and you can look at it, and then based on that, you parameterize your model. Now, if that first simulation is really off, you need to know something about your watershed. As I showed here, no amount of data really will help, because the more data you have, okay, the parameters will change again, and you put more data, it will change. You need to have some knowledge of your watershed that you can constrain the parameters. You say, well, this sub-basin here is infiltration dominated, I know that. So the CN2 can only range between here and here, and not let it, go wild and so on. So you need to have good knowledge. And so initially, yes, you really have to put, and probably discuss the the output.std. But after the first simulation, just a single simulation with your default parameters, you go to this file and you look at the numbers, see if they really make sense or not. So you can do adjustment based on your best knowledge of the system. And nothing can replace that knowledge that you have from the system. No automatic calibration can do that.
So it's okay if I have a model and I have good input data, but sometimes you have a situation all over the world that you have no coordinate station, so no at the outlet, so you cannot calibrate your model how to do that. But on the other hand, you have to model that area, or you want to model that, and so you have a lack of data, or the data are insufficient, or have a lot of errors. So is it possible to make any kind of calibration without having the discharge data for the outlet?
Yeah. If you have soft, Prof. Serini can make a comment that, but if you have soft information, if you don't know exact numbers and so on, but you know approximately what the yield is, you know what the crop yield should be approximately, you know evapotranspiration or something, and there is no region in the world that has no information. There is some information that you can gather that information to constrain your parameters and to come up with some reasonable numbers, I think.
I agree. The literature value, there are lots of literature value. Let's say I may be working on a watershed in Algeria. I may not have a watershed in Algeria, but I may have something in Tunisia that has got very similar climate conditions, similar rainfall patterns, similar crop characteristics. So you may be able to see a literature that will be published or a report that's published in Tunisia and use that information to calibrate your Algerian watershed. You're not able to calibrate on a month by month, on a day by day, but at least you're able to say, okay, on a long term, my ET is supposed to be, for all-in for ET should be 400 millimeter, and the model is saying 380, so we are getting pretty good results. But on the other hand, if the model says you need 800 millimeter water, then we know there's something wrong with it.
Okay. So that's another way of calibration. So you do not use your discharge at an outlet, so you use other information.
Yeah. We have done that repeatedly in the US. We don't have every watershed, even though it's extensively monitored. So we take a parallel watershed, a nearby watershed that's got a lot of similar characteristics, where this model, so we calibrate that watershed and then take the parameter from the watershed and apply it to the other watershed where we don't have data from. Okay? And always when you do that, actually, you always also report your uncertainty. I think Karim will cover that. Without model observation, you can still assess uncertainty based on the parameter that you're going to choose. So even if you don't have observation data set, you can still report your uncertainty, quantification of your uncertainty based on general knowledge, based on literature values, and things of that nature.
Okay, fine.
Yeah.
A good variable often is crop yield. Usually it's available, you can gather that information from the local statistics or whatever. If you have crop yield, then you know that your ET is okay. If ET is okay, then your infiltration must have been okay. If that is okay, then I don't know, groundwater reach soil water is about okay. So that can adjust many. Even if you have data, if you have discharge data can only tell you that how much water is runoff from the river, and a little bit comes back from the soil. Yeah, but it mostly it can give you a good idea of the runoff. Should we begin? Yeah. Any questions before we start? No questions? All right. So let me tell you a little bit more about the uncertainty. And in this picture, these points are the measurements. And the black line is the simulation. But this is the dream of every modeler to come up with something like this. But unfortunately, you will never get this. You will never get this for many reasons. The reason is that there are errors. There are errors in the input data that you use, rainfall, quite a bit of error here, really. You have land use, you have soil, and discharges, whatever. We model parameters, we model structure. I mean, the whole concept of model may be wrong, the parameters we don't know. So there is no reason to expect to get a perfect solution, right? And we don't usually. These are the famous words of Mr. Fox. He's a statistician, that all models are wrong, and but some models are useful, and hopefully SWAT is one of those useful models. Otherwise, well, it is wrong, yeah, it is, of course. And that's because there are processes that take place in the watershed, and especially with the distributed models, I mean, you have more of this situation, that there are processes in the watershed that they are not accounted for, or not accurately accounted for in the model, right? You have, I'll show you some pictures, you have a lot of waters coming into the rivers, you taken out of rivers that you don't even know about. Many things. And there are processes that are happening in the model, but we don't know they are happening in our watershed, you see. So there is all kinds of errors and uncertainties like that. And this is one, I showed you this already. So this is the conceptual model. This universal soil loss equation really is a very simple model. If you don't know, really it has a lot of problems with it. And then there is the modeler. I mean, there has been many studies where they gave the same problem or project to modelers of different modeling experience. And of course, at the end, they all give you different results. So it depends very much on the experience of the modeler, that how it turns out at the end. Now, in a watershed, let me show you some pictures here. Years ago, we had a project in China, and we wanted to do water quality, like sediment and discharge and all of that. After spending 2.5 years trying to simulate the sediment, we couldn't do it. We never got even close to the numbers that were reported. And then a year later, I went to the watershed in China, and it's near Beijing somewhere, and we went up and down to see what was happening in this watershed. And you see all kinds of activities in the watershed. You have a lot of road building activities and a lot of large erosions that they always clean up and dump it in the river. The stuff goes right into the river. You have these piles. You go, this is the Haihe River. You go through it and you see these. From road building, they put these piles, and then in the next storm, the fine material is washed away, and the coarse material, they take it again and use it for road buildings. And then these kids also are not helping very much, this putting sediment into the water. So you see so much activity, you know, a lot of dumping of material. Here is the river, and you see all these materials. So there is no way SWAT can account for this. And then you have all kinds of water management. You have really everywhere. And especially in China, there are a lot of rivers which are now canals, and they go this way in the morning and the other way in the afternoon. So it's really very complicated. And then all kinds of water management, and then you can get special erosion problems that you don't know about, and you might get special event. You have no water in the river, and you're wondering why you don't have water when the lake froze and there is no water coming. You may have special pollution situation that keeps sort of bleeding into the main river, and you cannot find out what is the source of this pollution. You may have a very strange situation like this, really beautiful. This is towards the source of Yellow River in China. This Yellow River, you come to a point that you see there is a blue and a yellow, and they merge together to form Yellow River later on. So it's not always very yellow, it's not always full of sediment, and if you have a measurement up there and a measurement down there, and you wonder, you know, what is going on here. So you have all kinds of dams and reservoirs and special situations. And in the watershed, if you are not aware of any of these, then this could really cause a lot of problem when you come to calibrating your model. So that's why we have all these errors and uncertainties. And this is a good example of Aswan Dam, and you see it went into operation somewhere around here, you know better than I do, this our colleague from Egypt, in 1968 or something. And then you see what happens before dam went into operation, and then after it went into operation. The downstream flow regime totally changed. So if you have outlets which are come downstream of the dam, then you really, there's no way you can really calibrate for that unless you know the operation of the dam. Now, for SWAT Cup, as I said, we started developing this program slowly, and sort of I try to put in some of the things that you need to know, or the tool that you need to have in order to calibrate a model. And I will show you some of those. With this model, you're able, this software, you can do calibration, you can do validation, you can do one at a time sensitivity analysis, you can do global sensitivity analysis. We'll look at this in more detail. You can do uncertainty analysis. You can visualize the watershed and outlet locations. I will show this. There is a Bing map in the program. Bing map is sort of Google Earth, but from Microsoft. And you can use that to actually look at your region and see, what the problem is, what is going on there. You can do parallel processing, as I said. There are a number of utility programs. There are upstream sub-basin. There's a program called Upstream Subbasins that calculates all the sub-basin upstream of an outlet. So you need that if you want to parameterize your model, you need to know what are the upstream sub-basins. And then there is make observation. I haven't put all of these into the software yet, but slowly. This is already in, but this is one of the files inputs that you need to make is your observation input. And it could be a bit tedious if you have a lot of observations. There's a program that can do that for you. And the elevation band is important. Sereni probably has already talked about it. You can have elevation band if you have a sub-basin with mountain and you have a climate station somewhere at the bottom, then really it should be adjusted as you go higher in the mountain. So it's not easy to do this in SWAT, in the ARC-SWAT interface. You probably saw that you can specify that sub-basin or sub-basin and all that. But there is a program that can simply do that for you very easily. I'll try to show you some of these, but the whole procedure for this SWAT Cup is that, first of all, it has 5 different programs in it right now. You can use the glue. I don't know if you're familiar with these, but these are algorithms that are very popular for calibration of hydrologic models. There is Parasol. Glue is sort of a Bayesian-based or semi-Bayesian-based program. You have Parasol that is based on shuffle complex. If you're familiar with these methodologies, there is MCMC, that's a Monte Carlo Markov chain, that's a fully Bayesian approach. There is SUFI2, and there is PSO, the particle swarm algorithm, which is sort of is based on sort of a natural behavior of a swarm of bees, for example, and how they optimize. So these programs are in there, and you can use any of them. Of these, probably glue is the simplest one, and MCMC the most difficult one to use. But they're all available, and you can use them. The idea is that, as I said, you have to generate parameters around the model. It's parameters around the model, and so on. So these, any of them, they can generate parameters. And then there is a program called SWAT Edit. This program puts those parameters into the SWAT files. And you know you have thousands of SWAT files you may have, and each parameter has to go exactly to the same, right, HRU and so on. So you need the program to do that, and that SWAT edit does that. And then you run the SWAT exe file, whatever version, 2009, 2012, so on. And then you get SWAT output. And then from the SWAT output, you've probably seen the SWAT outputs. Everything is in there. It's not easy to read these outputs, or sometimes even to open the files. You need some kind of an extract program so that it can extract from these outputs exactly what you want. You may have observation all over the place, you may have missing data and a lot of things. So this file goes and extracts those things which then you can compare with your measurements. And then it puts them into output files, and then these programs analyze that output and then come up with new parameters, and this repeats until some stopping rule is met for each program. You can download SWAT up from different websites, and I suggest that you check this every time you want to really use it to get the newest, the latest version, because I'm very rapidly changing and putting things in right now. And I will do it even more so in 3 months. I will take a year of sabbatical, which I plan to spend on this, and really develop this software even more. So you may want to check those sites and get the latest version. Now I'll tell you a little bit about the SUFI tool. It's a program that we developed initially. SUFI 1 was for smaller scale models such as macro and HITES and small hydrologic models, but then came SWAT, and you really needed a different philosophy for handling all these parameters and so on. So the idea with this software is that if I give you one input, a value for a parameter, you give that to the model, and the model gives you one signal for discharge, for nitrate, for whatever. Now, if I don't have a single value, I have a distribution. And the distribution, I show distribution with, it's a uniform distribution, it's a range. That's because you could have a distribution, say normal, gamma, beta, whatever distribution for each parameter, but for SWAT parameters, we really have no knowledge of the distribution. So the most general distribution would be a uniform distribution, which is a range. So you can say, for example, this parameter CN2 is from 30 to 90. This is also given by SWAT, gives a range for every parameter. So we use that range. So if I give you a range instead of a single value, then instead of having a signal as an output, you have a band of signals as an output that we quantified with the so-called 95% prediction uncertainty. So we get that by taking a sample from here, you run, you get one of those, you take another sample, you make another run, you take another sample, you take 1,000 samples from here and you run the program, and then at the end you come up with something like this. So I am often asked by people, and I have a very hard time getting the point across, that everybody is looking for the best solution. They ask me, what is the best solution? And I do give the parameters of the best solution, but I don't go any further. In fact, I don't think it's right, it's correct, or it's prudent, or it's, I think it's, you see, that different parameters can give you the same, more or less the same result. So there is really no best. There is a set of solutions and a range of parameters. So when you think of my solution, you always think of this, and then you compare it with the observed signal. But really, we should be thinking of this, and this is your solution. There is no best solution. There is a best range, but there is no best solution. So whatever that you do with the model, you need to propagate this uncertainty, always. So you have a model, you have a range, and then you want to see something else, or you want to see a scenario, do scenario analysis, whatever that you want to do, you have to propagate this to get the full solution, not just one of thousands of solutions and say this is my best solution. I think it's a little foolish to think that there is a best solution. So you have a range, and then you get a certain 95% prediction uncertainty. I'll show you how you calculate that. Now, if I give you a larger range, so a bigger uncertainty of your input, you will have a bigger uncertainty of your output, clearly. A bigger uncertainty. Now, at the beginning, I usually encourage that you make one iteration to see how things look like. You make one iteration. You can use a very large range, as large as SWAT gives you. SWAT gives you a minimum and a maximum. I use that as absolute range. So the program never allows you to go beyond this range. And this is in a file. You can edit that file and make it larger if you like, but anyhow, that would be the absolute range that the parameter can change. If you set all the parameters to the absolute range, and you run your model 500 times, and you get this as the output of SWAT, and then you get this as your observation, you know that this is not a calibration problem. You should not calibrate any further. There is no way you can capture, this is the full range of the parameter, and this is the full range of solution that SWAT gives. There is no way it's going to go over here. So if you have a situation like this, you have to go back, you have to redo your model. There's something not right there at all. So you immediately know if you can calibrate this model to make it better or not. This initially should be somewhere in here. And then you can try to narrow down this uncertainty band of your solution. So you want to get the smallest uncertainty. At the same time, you want this. These are your observations, right? This is all you have. Your observations should be within this. This is your model solution. And just as I showed that this would be the ideal case here, sorry, I said this was the ideal case that, oh, that's way back, so forget about it. I showed you the ideal case where all your observation was in on your simulation. So this is not your simulation. You want your observation to be in here. So if this is in here, then you're fine, because you're simulating all the observation. You're simulating all the observation. The problem is that you have a very large uncertainty. If you make this very large, then you can make this very large, and you can capture whatever. So the idea is to have this very narrow as possible, and yet to have all your observation points within this band. Then you can say, all right, I'm capturing all of the observation. There is a difference between error and uncertainty. There's a difference between error and uncertainty, and I'll show you what is error and what is uncertainty. Now, the concept is that in SUFI 2, you combine calibration and uncertainty analysis. They are not two different procedures. There is just one and the same procedure. Then you account for all uncertainties. Now, there is input uncertainty, there is model uncertainty, there is parameter uncertainty, all kinds of uncertainties. You try to account for all of these. It would be nice to do some kind of a deconvolution and to see how much of your uncertainty comes from the parameter, how much comes from the input, how much comes from the model. But this is very difficult to do. It's very difficult to do. So what we try to capture now is the full set of uncertainties by trying to capture most of your observations. If I have all of the observation in my prediction, then whatever uncertainty there is, I'm accounting for it because all the observations are within the prediction uncertainty. So, and the parameter uncertainties are depicted by intervals, a uniform distribution, and the output uncertainty is quantified as the 95% prediction uncertainty. It's 95 ppU. Now we calculate this at the 2.5% and 97.5% level of your simulations. So the bottom 2.5 and the top 2.5, they are sort of extreme situations, we leave that out. And that's how you calculate it. You have your parameter uncertainty. You use Latin hypercube to take samples. And then you give that to the model. You do this at 500 or 1,000 times. And then your solutions, at the end, you calculate your solutions. You do the cumulative distribution of every observed point. Every observed point will have a cumulative distribution of simulations. And then you calculate this 2.5 and 97.5%, and this is the 95% prediction uncertainty for any variable, for discharge, for nitrate, for anything. So that's the input, it's parameter ranges, and output 95% PP. Is that clear? I show you the Latin hypercube. If I can draw it here. So you have parameter ranges. So you have a parameter, the range. You have the second parameter. You have the third parameter. And you decide how many simulations you want to make. Say you want to make 4 simulations, for example. Then you come and you divide these into 4 equal intervals, every one of them. So this is 1, 2, 3, 4. And 1, 2, 3, 4. And 1, 2, 3, 4. And then you randomize these. You randomize it, so you get maybe 2, 1, 4, 3. You randomize this one, you get 1, 3, 4, 2. You randomize this one, you get maybe 4, 1, 2, 3. And then this, in the middle of this, you can take it in the middle of this, or you can take a random sample from this. And this one gives you one set of parameters, and then this gives you one set of parameters, so you get 4 sets of parameters like this. Now the advantage of this over Monte Carlo is that if I take 4 samples from here, they may all fall at this corner. I may not cover the whole range of the space of my parameter. So by doing this, it's sort of a clustered randomized sampling. That's by doing this. You make sure that you cover the whole range of the parameters, each one. And then you have 4 sets of data. Of course, you don't need 4, you make like 500 simulations or so. And if you go to the references for this Latin hypercube, when they test it, it's much more efficient than the Monte Carlo. So then you make the samples, and you run the model, and for each observation, you extract the data, and at the end you have 5 simulated points. For every observation, you have 5 simulations, 500 simulations. And then of these 500 simulations, you calculate the cumulative distribution, and you get the 95 PPU. Now, what happens? The whole procedure is that this is nitrate, and this is actual data from the tool. Initially, you may have a large range of some parameter, and then you take samples, you propagate, you calculate the 95 PPU, and that's the shaded area. And this is your observation. So you see, initially, I have a large interval of uncertainty for my parameter, and you can see that all the observation is within this 95 PPU. So this model is accounting for all observations. The problem is that I have a large uncertainty. I would like to decrease the uncertainty and yet account for all of these observations within my simulation. So I start decreasing. I decrease the So I start decreasing the parameter range, and this is what happens. Something not right. Anyhow, as I decrease this range, you see what happens? The prediction uncertainty decreases, but then I start losing observations. But this may very well be a bad observation. I don't know. So you have to account also that your observation may have a certain uncertainty itself. And then, as I go further, decrease the uncertainty, you see that now I'm really beginning to lose observations. And if my observations were fully correct in this case, then my model, well, it does account for some, but it doesn't account for most of the observations. It's not accounting for most of the observation, it's outside of my simulation band. So for this model, the uncertainty is this shaded region. This is the uncertainty. But then the error are all those points which is outside of this band. Those are errors. I'm not accounting for them. They are errors. So there's an error here. This is the peak should be over here. It's here. So if I continue here, at the end you get to this point. This is the so-called maybe best simulation, where you have one value, I have one signal, but then very, very few of my observations are being captured by this one value. So I need to sort of compromise here and maybe stop somewhere, that the uncertainty is reasonable, and yet most of my points are within this. So that's the trick, is to get a range that most of my observations are within this prediction. But this is my prediction. All right, so to do that, I try to, if you can accept this, that the observations reflect the net effect of all true processes in a watershed. Because you have all natural processes, they come to this observation. Given that your observation is correct, then this observation point is really all true processes translated into one single point. And if I'm able to account for this one single point in my simulation, then I'm correctly accounting for all those natural processes that are taking place. So, because that's the goal of calibration, is to capture, to account for the observations. Now, what that is, so the uncertainty analysis becomes to obtain a range of parameters such that upon propagation, the 95 ppU brackets most of the observed points. So that's, if you do a stochastic, and not a deterministic, that I have one signal as my observation and one signal as my simulation, then the idea is to come up with that parameter range that when I propagate it, I can capture most of my observation. That's the uncertainty analysis. No. Again, so this is the ideal situation, which we never have. But if you think of stochastically, you can have, you want to capture all these observations, you want it to be within your prediction. This is my model result. This is my model result here. This is my model result. Here, this range is my model result. And my model prediction accounts for most of the observation. That's the idea. But now, somehow, I need to quantify this. To quantify this, we have R squared, Nash subcliffe, root mean square, all of those objective functions can be used to quantify the fit, you know, the goodness of the fit here. But for this, we have nothing, or we didn't have nothing to quantify how good this is. So we came up with two factors. One is the P factor. That is the percent observed data bracketed by the 95% prediction uncertainty. We call this the P factor. And the best value is 1, of course, 100% of data within the observation band. And another one is the D factor, and that's the ratio of the average distance between the 95 PPU band. So it's this distance here, average over the entire thing. The ratio of that by the standard deviation of the measured data. So to sort of normalize this distance by the standard deviation of these observation points, and that gives you the D factor, and the best, of course, is 0, if this goes to 0. So just like R squared, the best value is 1. Here, the best value is if this is approaches 1 and that approaches 0. So I have a way of quantifying the goodness of the calibration and the uncertainty.
The average distance between is,
Sorry?
what you explain the average distance between the 95
Yeah.
is a width of the band?
The width, yes. The average width of this. The average width of
Now
this.
the distance with, to measure that is
Yeah.
the simulation.
It's simulated, yeah. For every point, you have the upper and the lower. That's the distance. You average that, you divide by standard deviation, and you get this factor. Now, again, somebody asked me what is a good value for Nystadt cliff. If you have, what is a good Nystadt cliff? Or what is a good R square? Any ideas? Well, yeah, the best value is 1. I mean, if you, in a calibration, you get R squared of 0.5, is that good calibration?
Sorry,
Depends.
there is a standard paper about standardization of calibration that hydrology model,
Yeah.
like for example in groundwater, there are papers for define the
Yes.
best value.
Yes. But that is very, subjective.
Yeah.
Depends who wrote the Morasi's paper, that's what you need. Morasi has a paper. But it's very subjective. Sometimes R squared of 0.2 is very good. Sometimes 0.8 is even not good. 0.99. So it's the same thing here. It just, if you have a R squared of 0.7, it tells you what it is. It tells you it's 0.7 from 1. The same thing here. So it's hard to define, what is really good. But, based on the experience and looking at these graphs, if you have P factor of around 0.7, 0.8, and if you have a D factor of around 1, then I would say this is probably okay. It's good. So subjectively, I can say that would be my idea.
Probably depends to the scale of the
Yes,
model,
depends,
the
exactly.
detail that I need.
Exactly, depends. If you're talking about sediment, if you get the R squared of 0.4, this is excellent, very good. But if you're talking about this much, you expect a bit higher and so on. So the whole structure is that you have these system analysis programs. They give you model in, you give to the model, it gives you model out. So that's the simple structure of the whole procedure. Is like that, and the interface is also like that with SWAT SUFI 2. If I expand that, you start with parameter file, and then you do Latin hypercube simulation, you get parameter values, SWAT edit puts that in the SWAT files, and then you run SWAT, and then you get the output, and so on. And then with SUFI 2, there is a lot of things that are modular, so after you run, you can extract outputs and so on. And then you calculate the objective function or the goal function, you calculate the 95 PPU, the different program. And then if you're not satisfied, then you update, you get new parameters, parameter ranges that you put in there, and you repeat this for a few iterations until you get.
Sorry, the program can analyze the correlation about the parameter. So I think if I use two different parameters to calibrate the model, probably if I the two parameters can be correlated with the solution, I can obtain the same solution with this, a couple of parameters.
Okay, yeah.
You can.
Yeah, you say if two parameters are correlated, and if one goes up, one goes down, so they go up, and you get the same thing. Yes. If parameters are highly correlated, just the way we sample here, each parameter is sampled independently, so you get independent sampling.
Yeah.
So you get the correlation table. I'm not sure if I'm printing that or I remarked that in the program because you can get large tables. You see that the correlation between parameters is very, very, very small because they are random sampling. If you have random sampling, then the correlations between parameters are small. But then, if you have parameters that you know are highly correlated, for example, there are some parameters that you really cannot fit together. Say the height of groundwater and the threshold of river. I mean, it's clearly these two cannot be correlated, cannot be, calibrated together. So there are some that you really need to avoid. It makes no sense to have them together because as height of groundwater increases, your threshold must increase. So there is no way you need to fix one of them, but then most of the other parameters, even if they are in reality correlated, but because you take random samples, these samples are not correlated. Samples are not correlated. The same with all of these procedures. Because they take random samples, so they are not, the samples are not correlated together. But if two parameters, you know that they are really correlated together, then you shouldn't calibrate them together.
Or you should suppress one, so here's the factor correlation.
Yes, if you know the relationship between the two, then you can just use one and then scale the other one. So any questions or thoughts? I have here a simple explanation of the other procedures, like here I have PSO and glue and so on, but I think maybe I shouldn't do this now. It may get a bit confusing. So I explain this, maybe I do that tomorrow and tell you a little bit about the other programs, the PSO and glue and MCMC and Parasol and so on. But what I want to do is show you the program. And then, when do we quit? When do you guys quit? Usually every day at 5? 5:20, okay. So we have an hour. What we should do is, now, I asked them not to download the program, not to install the program on your machines, because I wanted to give a new version of the program, but then it didn't make it. It's not ready, the new version. So I have to give you the old version, which is not so old anymore. So you don't have SWAT copy installed, I think, in any of these machines.
No.
So I give you 2 of these, and there is a directory that you should you have a data folder that you don't need to worry about that. Those are just some internal stuff that are kept there. You have external data. In the external data, you have example projects. In the example projects, I have worked out, or this is just something I was playing around with. You have a blue example, MCMC, Parasol, PSO, SUPI2, and just an example texting out. That's a simple texting out. Now, SWAT Cup is a standalone program. It doesn't interfere or need at all the ArcGIS or ArcSWAT. It's once you build your project and SWAT creates the texting out, right? For those of you who are new to SWAT, is if you build a project, and I have SWAT projects. So if your SWAT project you have built somewhere, and if you go here, I have an example project that I use. So this is what SWAT gives you, and if you go to the scenario default texting out. So the final step of SWAT before you make the simulation is to build this texting out file, where all of the SWAT parameters go into these files. So SWAT itself is a Fortran program, and it doesn't care about the ArcGIS or anything like that. It just reads simple text files. And all SWAT parameters are here. Your sub-basin parameters are all here. You see it looks really horrible, so you ask me. And all the soil parameters go here. And the function of SWAT edit is to recognize what parameter is where, and then to come and make changes to these values. Make changes to those values. So that's why it's itself a complicated program. And groundwater parameters are here, and sometimes the SWAT guys, they change these or add things, and I don't know, and the program doesn't work. So you have to also allow for that. If something doesn't work, it's probably that you have a different version of SWAT than what is covered here. So you have this directory where everything is here. And if you have made a run, I don't know how much really I should cover right now. If you make a run from within ArcSWAT, then you get a whole bunch of output files, and which is not here. I deleted them. You get a whole bunch of output files in this texting out. And what SWAT Cup does is make a copy of this in your SWAT Cup project. And then it'll bring everything. It'll bring all those output files. So if they are large files, then, and if you're short of memory, then you should delete those output files. But anyhow, so in this, as I was saying, in this example project, I have worked out projects I will show you again from the interface. And then you have an example texting out. Then there are references. These references are some papers. Mostly it's self-advertising. Most of them are own papers. But they do explain to you different procedures and so on. And in the manual, I suggest that that you should perhaps read this the tour paper, because it's quite a good paper, and it explains to you parameters, and let me see if I can find it. Just Journal of Hydrology, this tour paper, and if you want to know which parameters are important for what, I have a table here. So I I did explain a little bit, but here is a table that it tells you the parameters. Here it says parameters sensitive to all 4 variables. That's discharge, nitrate, phosphate, and sediment. Parameters sensitive to sediment only. Parameter sensitive to total phosphorus only, parameter sensitive to nitrate only. You may want to know some of these. And parameter sensitive to sediment and phosphorus. Anyhow, if you look at this, you get some information. So that's from the references, and then source data. Source data, it's something you should not change. This gives you all the source files, say glue. All of these softwares have the same format. There is a backup directory. Now, your default project, when you make in the ARC SWAT, you get text in out. That is your default, that project, all your parameters are in there. Hopefully you've given some thought to making those parameters and so on. So that is your default files, and parameters are in there. SWAT Cup makes a copy of this and puts it in this backup. So this backup has that text in out. And in this backup, because you make changes to the parameters, right? You're always changing the parameters. You make relative changes to the parameters, as I mentioned. You may scale hydraulic conductivity also up and down. So it's made relative to the values in the backup. So the backup, it's your original files that will never change. So your original files resides in that backup. And then at the end, you get your parameters which depend on that backup to find their true values. So that's the backup. And then there is an echo file. What the echo file has is every program when it executes, it echoes some of the inputs to these files. So if you have an error or something doesn't run, if you go there and look at the echo of that program, you may find some hints of what could be wrong and what, if there is an error and something doesn't run, you may find what the problem is there. And then there is a glue in. These are input files of glue, and glue out. These are output files of SWAT that go in there. And then you have a whole bunch of other execution files and some batch files and so on, which are so all you need to run glue. They're all here. And then you find the same format, say MCMC. Again, a backup, echo, MCMC in, out, and then files of MCMC. If you go to Parasol, exactly the same format. If you go to PSO, again, exactly the same idea and the same, more or less the same format. And Sufi 2 has a little bit more because, well, I have the code of Sufi 2 and I'm able to change it, but for some of the other ones I don't have, so I have this program which is compiled in 32-bit compiler, 64-bit compiler, 2009, 2012, and so on. I will provide for the other programs also. So that's why there is more files of SWAT. This is SWAT 2009 is here, SWAT 2012 is in here, 64-bit, 32-bit, it's all getting complicated with all these different versions and so on. And then there is a utility program. In this utility program, as I said, this is upstream sub-basin, but here you will have elevation band and so on and so forth. You get a few more programs later that go in here. So this is basically what you have. And then the rest are just some DLLs and some programs that we don't have to worry about that. Now, the thing is, in the external data, source data, and SWAT 2009, I have an executive version of SWAT 2009. there are many different versions of SWAT 2009. This is a 64-bit, or 2012. I know there are like 20 versions of different SWAT 2012 right now. And the version that I have here is just one of them, and they keep updating that. So you may want, if you have your own version of SWAT, you may want to come and replace this with your version. So that if you make new projects, you get the right version of SWAT. Or you can go directly to your project, SWAT project directory, and put the execution program of SWAT there. Right now I have just some version of it here. Okay, that's a little bit of detail about this. So once you have installed, you should get here an icon, this one. So if I execute this, hopefully SWAT Cop will run. And then you get such a layout. You can start here, and this is a list of your previous files that you're working with goes here, and you can make a new project, you can open an older project, and a number of other things that I will tell you. But let's start with, say, a new project. Now, at this point, maybe you can just watch me, and then you will have a chance to, I think it would be best if you just watch me explain things, and then you will have a chance tomorrow to practice all you want. So when you start a new project, you go next. The first thing it asks you is, where is your text in out? Now this text in out location, it looks for a directory called text in out, and anything else can be in there. But text in out should be in the string of that directory name. So you can browse, and now I have, I can simply go to my SWAT projects. That's why it's easy. I know where everything is, SWAT projects. In the SWAT project, I have different projects. There is one example project. I'm just going to use this. And the example project, yes, scenarios, and then default, and then there, text in out. So, select, next. It says SWAT version. You can have 2009 or 2012, whichever one. And then the processor, you could have 32-bit or 64-bit, depending on your machine. Then the next thing, it says which program you want to use. So you can use any of these programs. I'm just going to start with SUFI 2 again. Next, it says, what is your project name? Now, this here, because I chose a SUFI 2 program, the SUFI 2 SWAT Cop by default will go to the end of this name that I'm going to choose here. So I'm just going to call that if I spelled it correctly. And then it says, where do you want to put it? So I will just go again to my SWAT Cop projects, here, and I put it here. Finish. So what it's doing now, let me go there to SWAT Cop projects, and what's my project?
SWAT progress.
Sorry?
In the SWAT projects.
Why did I go?
You send it in SWAT projects.
Or did I put it in SWAT?
Yeah.
Mhm.
Exactly.
I made a mistake.
Full and Sophie SWAT cup.
Yes, I meant to put it in the SWAT cup, in the SWAT cup project. But it doesn't matter. You put it in the right place. Now it made a directory called pool.sufi2 SWAT cup. And now again, the backup. The backup is that takes in out. It's exactly brought whatever in that takes in out and put it in here. And then I have echo, which is now empty. I have a directory called parallel processing. It makes this, if you do parallel processing, then it will use this directory, but there's nothing in it now. And then there is Sufi2 in. These are the input files of Sufi2 and the Sufi2 out. These are the output files. And then it also put a copy of the text-in-out files in here. Because here is where things are changing, are going to change. It's important to keep that in mind, that the parameters that are in the files here are just at any moment is the last parameter set of your iteration, whatever you were doing. So it's not the actual files, the parameters anymore. And then it has all those text-in-out files, and then it has a whole bunch of Sufi2 programs that it needs to run. They're all here. So, to start this, you will get a default. You just get an example of how these files look like here. So if I start from here, it says calibration inputs. I start here, and the first one is parameter information. Now, the things that I have here, the parameters that I have here, this is just an example to show you how the format is. Right? It's not a suggestion. I'm not saying you should do this. I'm just giving you an example. You need to edit these files. Because I often get emails that says, you only have 4 parameters here, but I want to calibrate some other parameters. You know? Well, you just have to edit this for your project. And this is just an example that you can use. Now, in this file, you have a text view, you have a form view. And unfortunately, my screen is too small here, so you cannot see very well. But the parameters, initially, you may not know how to formulate these parameters, right? Like you want to calibrate some parameters, you may not know how the expression goes, how to write this. In the text view, you see the expression of this. It says a relative change of C and 2, which is in the management file, and this is some range here. Again, I'm not saying you should use this range. It's just, it's just an example. Alpha base flow and so on. Until you get to this dashed line, there can be anything in this file you like. The form view only reads up to dashed line. So actually, I would like maybe to include all of these parameters here. These are CN2, alpha base flow, groundwater delay, groundwater QMN, groundwater revap, ESCO. These are usually important parameters for discharge. And I also have, this is a snow parameter here. For no reason, as an example, I put it in here. So I have these parameters, and if I go to form view, now I should be able to see all these parameters here. Now you want to add some parameter. A lot of work went into making this form view. As you know, SWAT has a lot of parameters, and they come in strange formats and so on. So if I go here, I have the option of add a new parameter. If I add a new parameter, a parameter will go to the end of this file. If I insert a parameter, depending on where the cursor is, it will insert the parameter here. Not that the order is important, but you may want to keep all the soil parameters together for your own information. Or you could import new parameters. If I say import new parameters, it will go and import parameters from a parameter file that I will tell you later. Once you make an iteration, it will suggest to you new parameter ranges. If you say import, it will just bring those here. So it's just for ease of editing. But let me add a parameter here. So if I say add a new parameter. Now it will go here. These are all the SWAT parameters here in different files. So you have basin, chemistry, groundwater, HRU. So if I go to any of these, I will get the parameters which are in this file. If I go to chemistry, I get parameters here. If I go to groundwater, I get groundwater parameters, HRU, whatever. Management is a bit more complicated. In fact, it's very much complicated. And you have different management options. You have auto-fertilization, auto-irrigation, you have burn, you have continuous fertilization. All of those operations. So if I use, say, auto-fertilization, it will give me the parameters of auto-fertilization. I can say I would like to the auto-efficiency, choose this one, say OK. It will bring the auto-efficiency here where my cursor was, so it will add auto-efficiency here. It says file name. If I want a certain file, I can just put the file name here. But if I leave it alone, that means all the files right now. File extension is in the management. Replacement method, I can choose here. So there is a little explanation. If I choose R, it means relative. If I choose A, it means absolute here it says, but you can add something or subtract something from the existing value. And if I say V, it will just replace it with the value that I give to it. So it's auto-efficiency. Maybe I want just a value. I want a certain efficiency. It says what is the minimum. I say, well, I want this to be between 0.1 and 0.5, whatever, efficiency. And then I can choose the hydrologic group. For this, I can choose certain soil texture. I can choose land use. And I can choose certain subbasins. So I may want to just apply this to a certain subbasin range. And this window of mine is quite limited here. So I can say subbasin 1 to 15 only I want to do this. And then, so subbasin 1 to 15. Then I can choose the slope if I want. I can choose which layer. If it's a layered parameter, I can choose the layer number. And I can choose a number of filters. Right now, it applies to all of the crops and iterations and rotations and everything. But I can choose and say that, actually, I want to put a filter. I want to do that only if the ID, the fertilizer is, for example, elemental nitrogen, something like this. So you can put a filter here. So this should help you to choose your parameters from whatever SWAT files, because you don't know the whole range of parameters in your mind. So, but you can see all the parameters here. And then if I go to the text view, you see that it just wrote that for me. That's how the syntax is the auto-fertilizer efficiency. This is all operation. This is all rotation. Operation number 11, which is auto-fertilization, and only for fertilizer ID is number 1. Only if I'm applying elemental nitrogen, it should have an efficiency of this. And this only for subbasin 1 to 15, and the range is 0.1 to 0.5. So you see, that's how you do it. In the form field, form view helps you to actually make the expression of how you want the changes, and it comes here. So you can see it. You can see it easily here. And then, if you don't want it, you just delete it here, and it will be deleted in the form view also. So this is how you will choose your parameters. You can either just type it here, or if you don't know, you can again go here. You can, I can add a new, insert a new parameter, say whatever you like. From a plant maybe, I would like to say that the harvest index for this plant, you can again specify here. It says what is the crop name that you want to do it. So I can specify here. I say this crop should be whatever. The crop number, give a certain number, so crop number 12, whatever that may be, to apply, to make the changes to that. So if I come here, then it will ask at the harvest index to crop number 12 in the plant.that. Anyhow, you can play around with this a little bit, and then you get exactly the hang of it, how to make parameters. So I have now here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 parameters. All right, here I have 13 parameters, number of parameters it says. And it says a note here, the program only reads the first, because initially there was 4 here, it says the first 4 parameters. It's just an explanation of what it reads. If I say 13, it will just read the first 13 parameters, and it doesn't care what is the rest of this file. It could be anything. Number of simulations, you choose number of simulations. Say, let's make 20 simulations, but usually you may probably want to make 500 to 1,000 simulations. Let's say 20 simulations. So that's it for this file. I don't have all of my options up here. Anyhow, there should be a save and somewhere in here. Maybe you have it. You have more options. You can see more. So that's the parameter information file. And then you just go down here. The next is a file called SUPI2 SWAT edit definition file. It says starting simulation and ending simulation. I was making 20 simulations, so it's now 1 to 20. Starting is 1. This is useful for many reasons, and one is that if you're making 1,000 simulations and for some reason it stops at simulation 500, you don't want to start all over again. You can start from 501 and go to the end. So it is for that. But initially, you set it from 1 to whatever number of simulations you want to make. This file CIO, this is a SWAT file. This is a SWAT file. I put it here because you often want to know the date. You want to know the beginning date of simulation. There's some information here that you need to know. For example, it says the number of years to skip. You really need to know this. This is the warm-up period. You know this about SWAT, right? You should definitely have a few years of warm-up period because you don't specify any initial condition to the program. So you need to run it for 2 or 3, 4, 5, let's say around 3 years. You should at least run for about 3 years so that the initial condition is equilibrated with your climate information. And then what SWAT does is run from the date here. It says beginning date 1982. It runs 1982, 1983, and 1984. But it doesn't write this anywhere. It's not in your output file. This is just a warm-up period. It doesn't write it. If it doesn't write it in the output file, then SWAT CUP doesn't care about that date, but it doesn't write. It only cares about what it writes. And it writes from 1982, 83, 84, it writes from 1985. And in this example, actually, Let me change this to match our observation. This says 23 years from 82, but I know that our observation begins from 1990, so this is like this. 87, 88, and 89, they are run, but no record is kept. And the output begins from 1990. And what is the time step? 0. Time step is monthly. So the first record is January of 1990, right? Okay, this information I need to define how to extract variables from the output of SWAT. Then there is this absolute SWAT, what's the file called? Absolute SWAT values. These are the values that are suggested by the SWAT program for all these, all the parameters here in the SWAT. They have some suggested values for no observation. And then save all, close out. See, if I run it now, it will run much faster without that overhead. So you see it is much faster because it was extracting, I don't know, a few hundred files before. So that's how you would use the sensitivity analysis. You can start using that from the beginning. If you're unsure about a parameter, whether it is sensitive or not, so you just run it and you'll see. So the next thing I want to show you, and this is the part I like the most, is the outlet maps. Before this showed the outlets, but now it's much more. Oh, it says output, so I need the grid code. So here, if I zoom here, you will see that this subbasin, there is a river probably going through here, and there is a river over here. And what I wanted to show is that this complicated situation here, you have a dam. You have a dam here, and you have some outlets over here, which is, it's okay if they are not affected by the dam. But often if you're downstream of a dam, then you know that there is no way you can calibrate. It seems like some small rivers here, and that outlet is there. So let me go to another location, which is the dam. So again, you see this outlet is affected by this dam. So there is no way you can calibrate this. And if you look at the maybe I can find some of these here. This is the same, that's from a different project. So when you have situations like this, you have your observation here, you have your simulation here, and there is really no match between the two. And there is the outlet.
You know, even if you cannot get data from the NAM, still available.
Often, no. But yeah, if you can, then yeah, you can put the data in there. Or you can make that outlet into an inlet. But if you have data from the dam, after the dam, downstream of the dam, you have the discharge, you can give that to the program as input. Then you'll be okay with the rest of it. But often when these outlets are in a very strange situation, very complicated, and there is a lot of water management, you will see, you will not get good simulations. So in all situations when we have cases like this, and you go there and you see that you're either downstream of a dam or something going on. Here, also up here, we see there is a big reservoir and there is a dam. There is a dam here and a big reservoir, and that has an impact on the discharge downstream of the tank, so you get this. The further away you go from here, the better it gets. Also here, with the dam. The dam here, the location is over here, you can see in the middle of the town, but it should actually be here on the river somewhere. So
Should be where the operator lives.
hmm?
The operator is
Yeah, you get. So this needs to be corrected. Yeah. And you can use this tool for this kind of thing. So if your observations are really not good, I can go 68 with some of these and now here you see the outlet properties. Now whatever information you have in the DBF of this shapefile, you can see here. Right? If I go to that to the SWAT projects. Example, watershed shapes, right? That's the directory I opened. Now, whatever you have here, you have all of these shape files you can see there. And then, so the rivers, the subs, you can be able to see the temperature gauges, the rainfall gauges, and all of that. And whatever information in these DBF files, you will be able to see here and to zoom based on that, or do these different things based on that information. Here, again, another situation of really misplacement of this. On top of a house somewhere. Not very clear where that should actually be. Now you get a situation like this, you're not sure if this should be here or should this be on this, because you already have this outlet here. So you really have to go look at the area, tributary area, and run the program once, look at the simulated values and see if the observation should be on this or should it be on this river. So this is a nice tool to give you a feeling for your watershed. You can even, you get a general idea, when you have a general idea of the watershed, sometimes your outlet is near a glacier. You know it's affected by the glacier. Sometimes it's everywhere. Of course, you can use the ping map in different ways, and you can fly over your watershed. Now later on in these layers, there is here layers. You can check the Bing map layers. Bing map itself has quite a bit of information that you can use, and I will later put other information here. So to identify, I find a lot of information in the internet that shows you where the mines are for water quality, so you can tell, you know, the impact of the mine, where the mountains are, where the glaciers are, where the deserts are. So you will get a lot of information of different layers. If this is a protected area, if this is high erosion area, or whatnot. And then all of that information will help to parameterize and calibrate the model. Now let me go back to the beginning. Let's say you are at the beginning, and I'll be here and close this. So go back to our project. You have just opened your. Let me go back to this project. Now, what I want to do is really start all over again. Now I've been changing the parameters here. I've made some runs. I want to start from the beginning. I go to the backup. All my initial things are here. So I copy all of these, copy, and I paste them here. Now I'm back to level 0, and I want to know how to proceed with the parameters and all that. What I want to do is I want to run SWAT only once, without any changes, to see how my default project looks like. So I can just somehow trick the program. I can tell it that I only have one parameter, and that's CN2, and that is really, it's not changing. It's just going from 0 to 0. Probably take that. So it's no change. I want to make one simulation, and I specify one simulation here. I save all and close all. I hope this works. So I can make a I don't have to even do this, but I can run this. No change is being done. I can run the program. See, there's no change. And it ran once. I can run the post-processing. I look at my simulation.
Just
2 minutes? Okay. All right. We have 2 minutes, so let's just stop here.
Running once with the set the initial.
Yeah, I just ran once with the initial default values of the project. And then I want to see how it looks at the beginning. And then based on this, I will parameterize the whole watershed and then make it run. So we do that after lunch, and I hope there is time so you can play with it.
Yes.
did you speak that?
Looking into that.
Okay, no, it's good.
Yeah.
But there's nothing obvious.
No.
Yes.
Do not think about it. Did you look at manual? Yes. So manual goes through separate sessions that do that. Where you run through your own input file.
The Africa paper.
Actually, I'm running like that.
You already have the
No, that is just a program. You have to provide your own data. Your own data, input that and run it. Then you will create statistics. And based on the statistics,
any questions? So remember what we were doing, I made the first run with SWAT, right? You remember how I did it? I just set the parameters to one parameter, one simulation, and I made the simulation. And I just want to look at initially what it looks like. So I can see it for all, that's the second outlet, the third outlet, and the nitrate. Nitrate, let's not worry about the nitrate right now. Let's try to see if we can fix the flow. For this outlet number 1, you can see that the simulation is very much underestimated, right? The simulation is underestimated. So if I just look at the default run, I can say that what I need to do is increase the peak flow, for this to this outlet. So to increase the peak flow, what should I do to increase the peak flow? In this PowerPoint, the presentation that I use, I will give a copy of this to Fabrizio, and then you can he said he will put it on the website, and then you can download, so you have this. At At the end here I have a number of slides. Here. But these slides give you some idea that what you should do if you have different situations. Say, if you have a situation like this, where your observation is just under the simulated or overestimated here like this, and you would like to bring down the whole simulation, it tells you which parameters you need to adjust to achieve that. So if you're overestimating, you need to decrease the current number, CM2. You need to increase the soil water capacity, and you need to increase this ESCO, the compensation factor. So it gives you some idea when you look at the hydrograph, the Orson observance simulator, you get some idea of what you should do. And for different situations, you may have to change different parameters. So here, if your the base flow is too high in here, your simulated base flow is too high, then these are the parameters you need to adjust, and so on. You get the number of suggestions here. If you have a shift like this, if it's the simulated values is too late, or sometimes too early, you need to do the opposite of this, what it says here. If it is too late, then you need to do this. You need to change these parameters, as it suggests. This should help you to match them a bit better. So if you have the peak is too high, the base is too low, that's what you do. And then if you go through this, you get the same sort of suggestions for sediment, how to change the sediment parameters. You can see what happens if you are underestimating peak sediment. You get some suggestions, again, for sediment, different situations, high sediment yield, and so on. This is nitrogen. So what you do, if you have different situations with nitrogen and organic nitrogen, phosphorus, and so on. So you will find this quite handy when you come to doing this. So now let's try to do the same thing here. I will show you one, and then you can start doing this yourself, because unless you start playing with this tool yourself, it won't help if I explain even much. In this case, so I would like for subbasin number 1, I need to increase. Am I doing this? I forget now what blue was. Let me take this. Legend back. Okay, yeah. So that's my observation, and I'm underestimating. So I need to, what do I need to do? So the situation that I have is the opposite of this, right? Here I'm overestimating, and here I'm underestimating. So I need to do what the opposite of this. So I need to increase CN2 and decrease soil moisture, water availability, and decrease ESCO for that subbasin. So if I go back to my project, now I close this. Subbasin number 1. Subbasin number 1 is here. So it's only one subbasin, and that's number 1. So for that, it is simple. I go to the project, and go here. So I need to edit this for my project. Therefore, what I do is for subbasin number 1, I know I need CN2. I need ISCO. And I need soil water capacity. And this means only layer 1, but if I take this away, that will be all soil layers, so I will take that away. For all soil layers, I need to increase CN2. All right, I will increase it, let's say, 0.2, 0.4. Now this, I'm doing this arbitrarily, but this you could do a sensitivity analysis, as I showed, and be more precise on this range. I need to decrease these, so I will decrease it. It's a value. Well, I know that I should go somewhere 0.6 to 0.8. And I need to decrease these, so I will decrease it about maybe 0.4 minus 0.2. And I need to do this for subbasin number 1. Now, if you remember this, you need 2 underscores, and then you specify soil hydrologic unit if you want. If you don't want, then you just leave it out. Another 2 soil texture can be specified. Another 2 land use can be specified. Another 2 subbasin numbers can be specified. So I need subbasin number 1. So that's how I specify subbasin number 1. There. So for subbasin number 1, I made the adjustments to increase the flow. And then I have subbasin number 3. Now in here it seems like the peaks are a bit higher. Here is okay, almost okay. Here is too low. A bit higher here, lower here. So I don't know, probably the peak is about right. But the main problem here is the shift. This needs to be shifted a little bit to the right. You see here and here and here. Everywhere there seems to be a shift. Now this either has to do with the parameters or really with the rainfall. Because the rainfall in this case, I think it's not all that accurate, my rainfall. But right now I will try to see if by adjusting the parameter I can correct for this shift. But this could really be the rainfall because it's systematic. It seems like when the rainfall was recording or reformatting or whatever, there was a shift. So I will try to catch this with the parameters first, see if it works. And the parameters, so when there is a shift, what needs to be changed? So here. And the simulation is too late, right? The rise in the simulation is too late. And in here, it's too early. Okay, so and I will do the opposite of this. It says increase slope by 20%. Slope. So I need to decrease the slope by 20%. Now, this is a little bit old, this handout, and there is slope here. We don't have slope anymore. We don't have slope anymore. I can get help from this here. And that means the parameter. The slope is let's say it's 5 slope. It is this, I can search here. The slope is changed here to this. Okay, it's in the HRU file. Is the HRU slope. So in the HRU, this is the parameter. Okay, in this parameter, and here it said increase. I need to decrease. So I can make a relative change, but before doing this, I can go and see what it is right now, right? I have no idea what it is, so I will go to the file and see what is the slope in HRU file. Yeah. Average slope is 0.059, and for subbasin number 3, that's what I want to change the average slope. Subbasin number 3, 0.096. So I need to change that. Okay, I make a relative change. Then I make a relative change of decrease it by about 20%, it says. So I decrease it by minus 0.4 to minus 0.2. So between 20 and 40%. And I do this. Here it is. So I would like to do this for subbasin number 3, right? Here is outlet number 3, and outlet number 3 is here. So the flow comes from here into here. So outlet number 3 seems to have all of these subbasins in it, it appears. Now this is an easy project to see, but sometimes it's complicated. You don't know from where it's coming and going into where. For this, I provided here a program. Let me go to this here, and I have to save this sometimes. Now here's a program. It's called utility programs. There will be a number of programs that will go here. But right now, there is this upstream subbasins. What this program does, it defines for you, okay, right now, I don't have it, but this will be in here afterwards. So if you go to this utility program and the upstream subbasins, you have a definition file and you have an upstream from to. It says upstream from to and definition file. In the definition file, it says how many subbasins do you have, the number of subbasins. You remember we have 20 subbasins. And then it says the number of outlets and I should remove some of these comments here. The number of outlets. Okay, I will fix the comment. The number of outlets that you would like to see the upstream subbasins of, right? And we have 3 outlets. Well, I just put 4 outlets. Let's say we want to see all the upstream subbasins of these outlets. 1, 3, 7, and just put 18 in there. And then there is an upstream from to. There is a manual for this. And the manual says, if I open the directory of these upstream subbasins, you have number of files here. And it says README. So all of these programs will have a README file. It says this program finds all the upstream subbasins for a given outlet, or a number of given outlets. Input, you have upstream dot definition file, and then you have upstream from to text file. It says this file is from the SWAT database. Open projects.mdb file. Go to reach, copy the column from to into this text file. So I go to my project directory. This from to is a file that it's a network file that SWAT uses to route the flow. So it knows it goes from subbasin, this subbasin, into that subbasin, and then from the other subbasin comes to this subbasin. So this is something that SWAT uses to route the flow, and that's what I want to know, how the flow is routed, so I can calculate the upstream subbasin of an outlet. All right, so I go to this file. It's my go to SWAT project, and it's example project. So here it says the MDB file. That's the MDB file. And then open the reach, and you get from node to node. So all you do is copy this, and then go to the SWAT cop. And it's already here, but I can copy this into here. So now I have the routing pattern. I have the definition file. I said I have 20 subbasins, and I want to see upstreams of 1, 3, 7, and 18. And go to utility program here. Let's close this. Don't need this anymore. The finding is that because I put this in there before opening the project, it usually should be in there automatically. So let me once do say all now if I All right, so once you edit these two files and then you execute and the program runs, and what it gives you they don't work out there. All right, let me try this again. I got the wrong two columns. I need from and to. All right. Okay, now it's better. Now I will need to save this. Save all and close all. Then I go to utility and run the program. And then I should get this file. And this file, let me go to the text view first. It tells you outlet number 1. The upstream subbasin of that is just 1, as you saw, it's itself. Outlet number 3. All the upstream subbasins are here. These are the upstream subbasins. Outlet number 7 has these upstream subbasins. Outlet number 18 has 19 and 20. If I go to the project, you see that this is number 18. Upstream is 18, 19 and 20. So you come all the way down here. You go into 7, all of these go into 7, and they all go into 3, right? So if I want now to calibrate let's say for this, I only need to adjust these parameters here, right? Now if I want to do calibrate number 1, I need to only adjust the subbasin number 1. It's the same. If I want to do number 3, I need to do all the upstreams of number 3. Now you see that all of these go into 7, and then all of these again go into 3. So if I adjust it for 7, I don't need to do all of these again for 3. What I think I should do right now. And these parameters, notice, are not here, right? They're not here. So these are these are what I think I should do now to improve based on that first default simulation. Is that clear? Does that right? Make sense? Okay, save everything and close everything. And then, no, I would like to make no longer one simulation. How many parameters do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. So I end up with 16 parameters. And I'm going to make some, I don't know, 30, I should really make about 800 simulations, but I make about 30 simulations. But in order to make it go faster, I'm going to remove, I think we removed all those no observations. I don't need to worry about no observation now until I calibrate the model. So I will go to this engine here and extract. They are unchecked. Both, they are unchecked, so it's not running. So again, I 30 simulations. Okay. Don't forget this. Save everything, close everything. Now I have 4 CPUs. I'm going to take advantage of the parallel processing here. And so I have 4 CPUs. I'm going to make something that can be equally distributed. It's not necessary, but it's better to have maybe 32, so that each one does 8. Parallel processing. So I activated, when I activate this, this immediately jumps to 4 CPUs. So it recognizes my machine has 4 CPUs, but I don't have to use all 4. I mean, I can adjust it, but I will use all 4 CPUs, and then I start the run. Oh, I'm using trial version, okay. I cannot make more than 20 runs. With the trial version that you have, you can make up to 20 runs just to test it. Parallel, yes. But to take full advantage of it, you need to get the license. I didn't realize I had trial runs. But here you see what's happening. You have 4 processes started, and they're all working at the same time. And if I go here to the performance, you will see that 100% of the CPU power is being used now. So you can see, you see all of these CPUs are working at the maximum limit. So you really used and it's finished already. So it really is much faster. And then I go to post-processing. Okay, now it tells me because it only ran 20, instead of what I specified 30, it expects to see 30 simulations. So this gives me an error, it says simulation number 21 is missing. So what I do is I have to correct this. what I have to do is go here and say I only want to make 20 simulations. Save all, close all, and I'll just repeat this again.
When you talk about hundreds of simulations or thousands,
Say again?
when you talk about hundreds of simulations,
Yeah.
I mean that you are doing at the time, or is the aggregation
each.
of each
Yeah.
range different?
In each iteration, you make about hundreds of simulations.
In each, not only.
Yes, not all together, yeah. In this one, in this iteration, I think for this situation, you would make about 500, should make about 500 simulations.
But that's the sum of every iteration.
Yes, if you, usually with this Sufi tool, you don't need to make more than 3 or 4 at most iterations. So if you find yourself making 10, 20 iterations, you're doing something wrong. You don't need to make more than 3 or 4 iterations. And in each iteration, you should make around 500 simulations, or a total of at most 2,000 runs. But usually, you don't need that many iterations. So I did this. Now this is finished. Okay. And I do post-processing now. Do you want to save it? No, I don't want to save it right now. Let me have a look at it. So this is what I get. For the first one, you remember I didn't save the last iteration. Okay, that was my mistake. I saved one of the previous ones, but I didn't save the default, what I did before, and that was a mistake. I should have saved that. But anyhow, let's look at one of these previous ones. You see here, the observation was much larger than you remember, was much larger, and we wanted to increase the peak flow. So I think we managed to do that, right? Now our flow is much higher than even the observation. So did I overdo the parameters? Yeah, probably I overdid the ranges. Okay, but that worked. At least I can increase it. If I can decrease it again a little bit more and get it a bit better. And then for the next one, the problem was with the shift. Did I correct the shift?
Yes.
Yes? If you look at here, you look at here, look at here. Yes, I corrected the shift. You remember there was a shift? Let's see if you can see it in the previous one. In the previous one. Okay, previous one was okay. But here, if you remember the problem we had before, so we managed to correct for the shift. I think for this one at least. The seventh one was a bit more, the shift. The shift was a bit less, but not exactly, right? You guys don't believe me, do you? Alright, I'm going to delete all these previous iterations. Delete. Delete. Now I'm going to save this. Save iteration as iteration number 1. And now, just to make you believe me, let me close this. I'm going to go here. I will take the backup. I'm going to paste it here.
What you have there is what you run.
Sorry?
What you put there is
Yeah.
what you are running at the time.
Exactly.
At the time.
Yeah, what is in your project directory is just what you've done your last run parameters in there. So I put now the backup in there, and now I'm going to do what I did before. I just want to make, I'm going to make one simulation, and one, put everything to one. And I'll just put something here with no change. It doesn't matter, it could be anything. So I take this one and I copy it here and I say I want a relative change of 0, so 0 to 0. So I save off, close off. I'm going to make this one run. Let me get rid of this parallel, no, I don't see the parallel. And then make the one run. So I got my original run. Do you want to save it? Yes, I saved it. And make it 0. 0 means my default original run. And now you can compare output. Let me get this. And iteration 1. Output. So now you can compare. You see what it was before? My simulation was very low. By changing the parameters, my simulations are much higher now. So that gives me some, this is fixable. So I know that by changing those parameters, I can catch the peaks and all that. And then initially this was, you see this? There was a shift here, there was a shift here, there was a shift here, there was a shift here. You see the peak had shift everywhere, right? And now, exactly on. And I didn't even change, I changed for the 7, remember? I changed all, made the shift for outlet 7, but 7 comes into 3. So and now outlet 7, you see how large the difference is here? The difference is very large. Now, by making the changes, the difference is much smaller. You see, the difference is really much smaller now than it was before. So it tells me that, so some of this shift I could do with parameters, but maybe not all of it for this number 7. I can go on increasing the slope and all that, right? What I did before, I can increase a bit more, but probably what happens at the number 3 outlet, that will probably go over, and so on. So the part that I could fix with parameter, I can fix it, and there is some which may be due to rainfall, I don't know. So with such a procedure, I can repeat the same thing again, and each time now I have some suggested new parameters, which are here.
Then the way of changing your concentration time is by changing the slope.
Right. That's one way. Changing the
You don't have any other parameter, I don't know, multiplier or something.
What other parameters are important? You know?
For the time of concentration that you can change, or add some other. I mean, it seems weird to change the slope.
It's strange to change the slope.
It seems weird, maybe it's not.
Yes, that is not one of the first things you want to change. The slope. But then it depends how much do you trust them, how much do you trust the other input parts.
You have to also provide the depth of the in SWAT at the beginning for the average slope.
Yeah, those are all calculated based on them. So if your them is good and the them here, I don't know what the resolution of this is.
Gives me an error. It says the given parameter sol underscore AWC was not present in the dictionary.
Well, you probably have a mistake the way you wrote the parameter here. If it says it's not present, then the way you wrote it here, if you check, this one you mean?
Yeah.
Okay, you probably wrote it incorrectly.
I copied it from the example.
Yeah. If it gives you that error, then you, let me see your, yeah, it's because you deleted the bracket altogether. There are parameters which have layers in SWAT. Those parameters which have layers need to have a bracket. If you delete the bracket, you won't like it. So,
empty bracket means you are using all the layers.
sorry?
Empty bracket,
Yeah, empty bracket means all the layers.
all the layers.
Yeah, if you want some specific layer, then you write in there.
Like
1, comma, 3, or 1 dash 5 means 1 to 5, and so on. So, let me stop here and let you take over. And where you installed, if you remember where you installed the program, there is an example texting out. You may use that. You may use the texting out that you made in the SWAT workshop. I don't know if there you did a project. You can use that texting out if you have some observations and so on. Or if you don't have observations, you can just try to set it up. But you need to have some observations. Or if you have your own project, then start working on your project. So you need, or use the texting out that I gave you and the observation that is here already, that comes with it, and see if you can just set up from the beginning and make a run and change the parameters. Unless you use it yourself, you can't really get the hang of it. You need to use it. So go ahead, just use it, and if you have your own project, then it's good. You look at your project.